Welcome back. This is Ink, and in today's problem, we're going to exercise the method of nodal analysis. We did a few videos on those. You can find that on the channel in the playlist section. So in this case, we're going to exercise what we've learned. But first, we want to compare it by using a different method. That method is finding the equivalent resistor seen by the terminals A and B, and then determine, or you can call it the equivalent resistance seen by the voltage source, and then use that to determine the current I. After that method, we're going to apply nodal analysis, which is the method we've been using in the previous videos, and determine the voltages at each terminal, and then use that to find or determine I. So in this case, we start by using the equivalence method. So we see that looking on the original circuit, so if I can find a pointer right here, laser pen. No, that's not what I need. That's not what I need. Oh, I think it's what I need. Okay. So in this case, I've never used the laser pen. By the way, this app is so cool. It's called Colanote. I don't quite remember if it's for iOS only, but it is awesome. So moving back to the video. So when we look, these two resistors are in series, so that adds up to 2R. Moving again, we see that these two are in series, so that adds up to 2R. These two are in series, and that adds up to 2R. Observing the circuit to the right of the original circuit, we notice that we have a Y configuration on the top, and we name this one 1, this 2, and this 3. So moving over to the left, and we're here, we say in Y to delta configuration, and this equation is kind of like just a thing of mine. So I call the top of it the sum of the products, and the bottom, that's the resistor, the target resistor. So RA in this case, so we're going from Y to delta, the sum of the product. So the sum of the product for the circuit, or well, the piece of the circuit, which is the Y configuration, we now say that R1 times R2, which is right here, 2R times 2R. Then we say R2 times R3, which is 2R times R. And then we say R1 times R3, which is 2R times R. That equals to 8R squared. The target resistance is 2R, or the target resistor is 2R. So that simplifies to 4R. Moving on to RB, we know that the sum of the product is going to equal to 8R squared. The target resistor, 2R, simplifies to 4R. 2RC, still same sum of product. However, this time R3 is going to equal to 1R, which is right there, which we get 8R. In the delta configuration, we're looking here, the delta configuration, C in the delta configuration is going to equal to 8R. Then A is going to equal to 4R, and B is going to equal to 4R. So we now move on. We see that the circuit can be simplified a little bit more. So in this case, scroll down a little bit, and we see that, let's go back up. We see that this 4R and R is in parallel and in parallel. This is because both ends of the resistor is connected, same terminal, and in this case, same terminal. So parallel for two resistor, the equation for parallel resistor, in this case 2, is both resistor, the resistor, okay, so 4R times R, which is if you have R1 and R2. So let's call R1 and R2 two resistors in parallel, so that's 4R times R, and the sum of the resistors. So that's 4R squared all over 5R. That's simplified to 4R over 5. And because this is in parallel and this is in parallel, and they're of equal well, not of equal value, but for R and R, both side. So B and A are going to equal. We then move on. We now see that we have a delta configuration, and to further simplify the circuit, a Y configuration would be more applicable. This is because if we had a Y configuration, we then could simplify the circuit much further. So in the delta to Y, I call the numerator the interchanging products, and then on the bottom I call that the sum of the resistors in the delta. So here, a little bit of like my interchanging product method is that I interchange each product in the numerator. So you would have, for the first product, you'd have RB times RC. Second one, you'd have RA times RC, and then you'd have RB times RA, or you can do it back and forth. They can interchange. So for R1 in the Y, so this is the Y that we're focusing on right now. So we're dealing with R1, which is this Y, well, this resistance. So we see that the interchanging product is these two. So we multiply those together. The sum of the resistors in the delta is going to equal to 48R over 5. That simplifies to 2R over 3. And moving on to R2. R2 is RA times RC, which is this. Simplifies to 2R over 3. And R3 is RA times RB all over the sum, which is R over 15. We then see this circuit right here, which is pretty much easy to simplify. We just combine these in series, combine these in series, and then do a parallel configuration, and the equivalent resistance comes down to 2.43 ohms. In this case, I have R. Well, let's keep it like that because we've got variables, correct? They gave us R, and they gave us the source voltage as V0, so let's keep it as R. Now we move. I is basically the the voltage source divided by the resistance seen by the voltage source, and that is 0.41 VO over R. We're dealing with variables, so let's keep it like that. Don't mind this right here. I was trying something. Now let's move on to using node method. So this is what we've been practicing, correct? So in order to find the current I, we'd want to know the voltage of the voltage source, and we want to know the equivalent resistance. In this case, we don't have to figure that out. We can apply our terminals. There's not one terminal where we can pick and just apply a super node or just do it in one. So we'd have to apply multiple terminals and apply KCL. So this terminal, we're going to call it V1. We can call this V3, or let's call this V2. Let's call this one V3, and let's call this V4. In this case, we're going to apply KCL at, let's apply KCL at node 1. So KCL at node 1, terminal 1 I like to call it, or V1. We see that V1 with reference to V2. So V1 with reference to V2, we're taking V1 minus V2. So that is V1 minus V2 all over 2R, because we have R plus R. So that's 2R plus V1 in this case. And let's just do V1 with V3. So V1 with reference to V3. So that's V1 minus V3 all over R plus V1 with reference to V4. And that's all over 2R. And that's equal to 0. We then move on to terminal 2, where we say from terminal 2, we can say V2 with reference to V1 all over 2R plus V2. We're just going backwards with reference to 3 all over R plus V2 with reference to V0. And that's the source voltage, and we see that we have a 1 resistor in that branch. So then we move to terminal V3, or node V3 if you want to call it that. So V3 with reference to V1, V3 with reference to V1 all over R plus V3 with reference to V2 all over R plus V3 with reference to V4, and that's all over R plus V3 with reference to ground. But in this case, so as always, we should always have a ground. So let's just call this our ground. Doesn't matter where we put it, as long as it's not between two terminals or two, what should I call it, node? Yeah, two terminals. So let's just keep it like that. So and that's all over R, and that's equal to 0. Forgot a 0 up here, so let's place the 0. And then we have at terminal 4, we have V4 minus V1 all over 2R plus V4 minus V3 all over R plus V4 with reference to ground. You could say V4 minus 0 volts, but you know, just say V4 all over 2R. And that's equal to 0. So as you can see in the first part of the problem, I had written down everything before start the video. So this is just a little bit of algebra gymnastic. Simplification will lead to 4V1 minus V2 minus 2V3 minus V4 equals 0. And then V1 plus 5V2 minus 2, that's a 2, minus 2V3 equal to 2V0. And I'm doing them in order, by the way. Minus V1 minus V2 plus 4V3 minus V4 equal to 0. And V1 is minus V1 minus 2V3 plus 4V4 equal to 0. So simplification, these lead to these. And then simultaneously solutions, or simultaneous solving these simultaneously will lead to the solutions. V1 is equal to 0.35 volt. And in this case, we didn't get a total volt. We didn't get a constant for the voltage source. So let's call this V0. V2 is equal to 0.59 volts. V3 is equal to 0.29 V0, and V4 is equal to 0.24 V0. Notice that the voltage drop across each branch of the circuit, if we add those up, we get the total voltage of the source. But in this case, we want to find the current I. So we're going to use V2, or just we can say V0 with reference to V2 divided by the R in that branch where the current I is flowing. So in this case, I is going to equal to V0 with reference to V2 all over R. And if we factor out V0, 1, and minus V2, which is 0.59, that is going to be divided by R. And we see that I is equal to 0.41 V0 over R. And by node voltage and putting those in your calculator. Simplification leads to the same expression we obtain for the current I by using the equivalent resistance method. So it just comes down to, as a circuit analyzer, which tool is best fit for the task at hand. And for the task at hand, we didn't have much current sources, so we see that we have a bunch of resistors and a voltage source. So node voltage is the best method in this case. Thanks for watching. Please subscribe and share and like. Thank you. See you in the next video. Bye.